मे आई स्टार्ट। राष्ट्रीय विज्ञान संग्रहालय परिषद संस्कृति मंत्रालय भारत सरकार के अंतर्गत एक स्वायत्त संस्थान है। हमारे इस संस्थान के अंतर्गत 25 विज्ञान केंद्र, विज्ञान संग्रहालय एवं तारा मंडल का एक नेटवर्क है, जो वैज्ञानिक दृष्टिकोण से ओतप्रोत एक संस्कृति, एक वातावरण हेतु देश भर में कार्यरत है। आंचलिक विज्ञान केंद्र गुवाहाटी इन 25 संस्थानों में से एक है और इसके द्वारा आज एक ऑनलाइन व्याख्यान, ऑनलाइन लेक्चर 125 ईयर्स ऑफ एक्सरे का आयोजन किया जा रहा है। आज के इस कार्यक्रम में मैं सुरेश सोनी, आंचलिक विज्ञान केंद्र गुवाहाटी की ओर से आप सभी का हार्दिक स्वागत करता हूं। आज के समय में एक्सरे का नाम बहुत आम हो गया है। एंजियोग्राफी, मेमोग्राम, सीटी की बात करें या बात करें एयरपोर्ट या अन्य स्थानों पर सुरक्षा को सुनिश्चित करने और स्मगलिंग जैसे कृत्यों को रोकने के लिए किए जाने वाले बैगेज स्कैनिंग इत्यादि की। आज किसी भी तरह की चोट का सटीक आकलन करने के लिए डॉक्टर सबसे पहले एक्सरे करवाते हैं। आज एक्सरे की बदौलत ही हम अपने शरीर के भीतरी हिस्सों को भी साफ साफ देख सकते हैं। लेकिन सोचने वाली बात यह है कि पहला एक्सरे कब, किसका और किसके द्वारा किया गया। आज से 125 वर्ष पूर्व 22 दिसंबर सन 1895 को वैज्ञानिक रोंजन द्वारा अपनी पत्नी वाइफ ब्रथा के बाएं हाथ का, लेफ्ट हैंड का एक्सरे लिया गया। अब बात आती है कि वैज्ञानिक रोंजन कौन थे और उन्हें एक्सरे के बारे में जानकारी कैसे हुई। रोंजन एक भौतिक विज्ञानी थे। 22 दिसंबर सन 1895 से महज 44 दिन पहले, यानी 8 नवंबर 1895 1895 को रोंजन अन्य वैज्ञानिकों के प्रयोगों को दोहराने के लिए अपनी प्रयोगशाला में कोशिश कर रहे थे। उसी दौरान बड़े ही आकस्मिक रूप से अनायास ही एक्सरे के बारे में उन्हें जानकारी हुई। इसी महत्व को देखते हुए उस दिन विशेष यानी 8 नवंबर को पूरी दुनिया में अंतर्राष्ट्रीय रेडियोलॉजी दिवस, इंटरनेशनल रेडियोलॉजी डे के रूप में मनाया जाता है। सन 1901 में रोंजन को एक्सरे पर महत्वपूर्ण कार्य के लिए भौतिकी का, फिजिक्स का फर्स्ट नोबेल प्राइज दिया गया। जिस तरह आवर्त सारणी पीरियोडिक टेबल में 99th एलिमेंट का नाम आइंस्टीन के सम्मान में आइंस्टीनियम, 102वें तत्व का नाम नोबेल के सम्मान में नोबेलियम रखा गया है, ठीक उसी प्रकार 111वें 111th एलिमेंट का नाम रोंजन के सम्मान में 2004 में IUPAC द्वारा रोंजेनियम रखा गया। एक्सरे वास्तव में इलेक्ट्रोमैग्नेटिक वेव स्पेक्ट्रम का ही एक हिस्सा है, जिसकी वेवलेंथ रेंज लगभग 100 एंगस्ट्रॉम से 0.01 एंगस्ट्रॉम होती है और हम कह सकते हैं कि इसकी वेवलेंथ 1 एंगस्ट्रॉम कोटि या ऑर्डर की होती है। 1 एंगस्ट्रॉम मीन्स 1 मीटर के 10 अरबवें हिस्से के बराबर। और रोचक बात यह कि क्रिस्टल्स में परमाणुओं के बीच की स्पेसिंग अंतराल भी उसी ऑर्डर का होता है और यहीं से शुरू होती है एक्सरे की बारे में हमारी जो यात्रा है, किस तरीके से हम उसको सोचते हैं, उसकी कहानी। धीरे धीरे टेक्नोलॉजी के साथ साथ इसी क्रम में चलते हुए एक्सरे डिफ्रैक्शन, XRD, एक्सरे इमेजिंग, एक्सरे फ्लोरोसेंस जुड़ते जाते हैं। और बात हम करें मटेरियल रिसर्च की या मेडिकल रिसर्च की, एक्सरे ने इन रिसर्च के आयाम ही बदल दिए। अब चाहे दांत का दर्द हो या रिसर्च लेबोरेटरी, एक्सरे का नाम अपने आप में इतना महत्वपूर्ण, इतना खास हो गया है कि हर जगह इसका नाम आना बहुत ही आम बात है। कैसे 125 वर्ष पूर्व एक आकस्मिक, अनायास घटनाक्रम प्रयोग घटित हुआ और कैसे उसने हमारी रिसर्च एवं सामाजिक जीवन दोनों को ही एक नया आयाम दे दिया, इसी को आज के व्याख्यान के दौरान सुनेंगे। आज के व्याख्यान 125 ईयर्स ऑफ एक्सरे के रिसोर्स पर्सन के रूप में हमारे साथ मौजूद है प्रोफेसर YK विजय। व्याख्यान शुरू होने से पहले मैं सर का एक छोटा सा परिचय देना चाहूंगा। प्रोफेसर वाई के विजय वर्तमान में प्रेजेंट डायरेक्टर के रूप में अपनी सेवा सेंटर फॉर इनोवेशन इन साइंस टीचिंग CIST IIS यूनिवर्सिटी जयपुर को दे रहे हैं। इसके साथ साथ बतौर प्रेसिडेंट इंडियन एसोसिएशन ऑफ फिजिक्स टीचर्स IAPT रीजनल काउंसिल 6 को भी अपनी सेवाएं दे रहे हैं। इससे पूर्व वे बतौर वाइस चांसलर विवेकानंद ग्लोबल यूनिवर्सिटी, बतौर डायरेक्टर सेंटर फॉर डेवलपमेंट ऑफ फिजिक्स एजुकेशन यूनिवर्सिटी ऑफ राजस्थान, बतौर डायरेक्टर सेंटर फॉर नॉन कन्वेंशनल एनर्जी रिसोर्सेज यूनिवर्सिटी ऑफ राजस्थान, बतौर डिप्टी डायरेक्टर यूनिवर्सिटी साइंस एंड इंस्ट्रूमेंटेशन सेंटर एवं बतौर प्रोफेसर डिपार्टमेंट ऑफ फिजिक्स यूनिवर्सिटी ऑफ राजस्थान को भी अपनी सेवाएं दे चुके हैं। आपका रिसर्च इंटरेस्ट लेबोरेटरी इंस्ट्रूमेंट्स डेवलपमेंट, इंटरेक्शन ऑफ रेडिएशन विद मटेरियल, थिन फिल्म्स, ऑप्टिकल, इलेक्ट्रिकल एंड गैस एड्सॉर्प्शन, पॉजिट्रॉन एनहिलेशन, पॉलीमर नैनो फिल्टर्स और गैस प्यूरिफिकेशन इत्यादि में है। आपने रिसर्च क्षेत्र में अपना योगदान देते हुए विविध फेलोशिप्स जैसे CSIR JRF, UGC सीनियर रिसर्च फेलोशिप, SIDA फेलोशिप, INSA फेलोशिप, ACU फेलोशिप, ICTP विजिटिंग फेलोशिप इत्यादि का सदुपयोग किया और विविध अवार्ड्स प्राप्त किए। और अभी मैं वर्तमान में ज्यादा समय न लेते हुए हमारे आज के जो रिसोर्स पर्सन है डॉक्टर वाई के विजय, उनको स्टेज मंच हैंड ओवर करना चाहूंगा और सभी से रिक्वेस्ट करूंगा कि ये सर का सेशन कंप्लीट होने के बाद एक क्वेश्चन आंसर सेशन भी हम रखेंगे। उसके दौरान आप सर से क्वेश्चंस पूछ सकते हैं और एक क्वेश्चन आंसर सेशन को हम आगे कंडक्ट करेंगे। लेकिन जब तक सर का सेशन चलता है तब तक मैं आप सभी से रिक्वेस्ट करूंगा कि कृपया अपना माइक ऑफ रखें। सर, नाउ स्टेज इज
Yes.
योर्स।
Okay. Thank you so much, Suresh ji. It was good morning and wonderful time, December 28th. And I'm really delighted to share with you whatever brief you have described about Ranjan and the X-ray. I'll try to narrate with pictures and diagrams and some models how important is that discovery. After 125 years, it has changed the life of human being. So I thank you very much for giving me this opportunity that in this platform of National Science Museum, uh, whatever we can share with the people and the students and the teachers about the X-ray, uh, it's a great pleasure because X-rays यदि नहीं होती, if there were no X-ray, आज की जो हमारी लाइफ है किस तरह की होती ये हम सोच नहीं सकते। इन द कोविड सिचुएशन व्हेन यू गो फॉर डायग्नोसिस ऑफ योर ह्यूमन बॉडी, it takes a long time, but the X-ray machine gives you instantaneous results. So that is what is the power of X-ray, and that is what we like to share in the present context. In 125 years, how the lifestyle has changed of the people regarding use of X-ray. So let me share my presentation through the slides. Can I have my slideshow?
सर आप प्रेजेंट कीजिए।
Okay. My presentation is there. Is it visible?
नो सर, विजिबल नहीं है.
विजिबल नहीं है. हाउ डू यू एक्सेप्ट इट, शेयर इट? पहले
सर
मेरे
जस्ट क्लिक
स्क्रीन.
ऑन प्रेजेंट नाउ.
हाँ,
जस्ट क्लिक ऑन प्रेजेंट नाउ.
यस, ओके. प्रेजेंट नाउ. एंड इसमें
जस्ट
3
ओपन योर
ऑप्शन आ रहे हैं.
पीपीटी. यस
हाँ,
सर, जस्ट ओपन योर पीपीटी.
पीपीटी तो खुली हुई है. इज इट विजिबल?
नो सर.
नहीं. तो ये एक्सेप्ट नहीं कर रहा है. पहले मेरी विंडो आनी चाहिए ना. अभी खाली आपकी स्क्रीन आ रही है. हाउ डू आई गो टू माई स्क्रीन?
सर क्लिक ऑन प्रेजेंट नाउ.
प्रेजेंट नाउ क्लिक किया.
यस सर.
एंड एंटायर विंडो.
नो सर, जस्ट ओपन योर पीपीटी.
पीपीटी तो खुला हुआ है मेरा. तो वो शेयर वाला बटन नहीं चालू हो रहा है. इसमें प्रेजेंट नाउ में जो शेयर वाला बटन है ना, वो चालू नहीं हो रहा है. तो आई एम
सर
नॉट
जस्ट प्रेजेंट
पार्ट
नाउ,
ऑफ दैट.
क्लिक ऑन प्रेजेंट नाउ and
प्रेजेंट
click on
नाउ.
a window.
ए विंडो. ओके.
Yes sir. After that, just select your PPTs.
ओके. ऑलराइट, ऑलराइट, गुड. इज इट ओके नाउ?
Yes sir.
Is it visible? Is it visible?
Yes sir, visible.
Yes, it's visible.
Okay. So thank you. So my presentation is regarding 125 years of X-ray discovery, how things have changed, our lifestyle. So I'm presently working at the Center for Innovation in Science Teaching at IIS University, and I'll be sharing my experience and learning regarding the X-rays, its a science and technology, and how it is useful for the mankind. In fact, William Röntgen discovered X-ray long back in 1895, so we are completing almost 125 years, and the first Nobel Prize in physics was awarded in 1901 to William Röntgen, and after that, several Nobel Prizes were awarded regarding the use of X-ray in other science and technology. Like the Bragg's was awarded a Nobel Prize for the Bragg's law to study the diffraction. The photoelectric effect was also discovered after this X-ray hitting a material and the electrons are ejected. So another Nobel Prize was awarded. And as the X-ray gets scattered, the Compton scattering phenomena was observed, and again Nobel Prize awarded in 1921. And the XPS, the X-ray induced photoelectron spectroscopy, was also discovered, and the elemental analysis using this electron as a ESCA, and the Nobel Prize was awarded in 1980 to Sigma. So almost in 80 years, several Nobel Prizes have come out of the discovery of X-ray. This is the picture of Ranjan, and this is the accidental picture when he was doing the experiment in the laboratory, and the photographic plate with a ring, everything was so visible on the screen, and he was surprised to have such a wonderful radiation which can penetrate even the human body. As we know by now that the X-rays are electromagnetic waves in the range uh, between 1 Armstrong and 0.01 Armstrong, and the energy in the range of 1 keV to 100 keV. So most of the X-ray sources are having the energy in the range of 1 keV to 100 keV. These are electromagnetic rays, and they can travel in a straight line like laser beam, which we see normally, which is a visible light. But this radiation is not visible. Visible radiation fall under this category around 400 nanometer to 800 nanometer. The X-ray source, typically the X-ray source is a vacuum tube in which the electron beam bombards a metallic target and results into the X-ray. This has got certain high voltage to accelerate the electron, and the energy is converted into energy of the X-ray beam. This was discovered and known as the Colles X-ray tube for producing X-rays. And when we see the energy spectrum or the wavelength wise, intensity versus the energy spectrum, we get a continuous X-ray right from a minimum to the maximum wavelength, and a line spectra as a characteristic X-rays. So these are basically varying as we change the tube voltage. When we change the tube voltage, then the minima also changes, and even at some stage, depending upon the target, which target we are using, a particular characteristic X-rays are emitted from different targets. For example, we are having a copper target, so around 8.9 kV X-ray characteristic line is observed. If you use tungsten target, then the energy is something like 18 kV or so, and so on. So this is the basically fundamental law, that with the voltage and with the Z of the target, we can get different amount of intensity of the X-ray produced from a given material. And this is basically governed by the Moseley's law, that as we change the Z of a target, then the lambda which is coming out, the characteristic X-ray, that changes. So for example, low Z material like chromium, iron, the K alpha has a wavelength, long wavelength, but as the Z increases, the lambda decreases. Okay. And if you go for tungsten, we still get a very high energy X-rays with small wavelength. This is the typical geometry of the X-ray tube, in which the filament is there, which is of course a tungsten. When we flow current, the electrons are emitted by thermionic emission, and in vacuum chamber, once the electrons are accelerated to the target, they liberate X-rays. And the X-rays are coming out of this tube through these windows. Although they are scattered in all possible direction, but we are having a small window, beryllium window, through which we can use these X-ray for any experimentation. This is how the typical geometry looks like. These are the beryllium windows, and this is the glass vessel through which the filament and the target assembly is assembled. The filament geometry is linear, so most of the beam comes out in a particular direction, that is called the point of focus. the target get heated up because of the electron kinetic energy of the electron beam, and therefore its intensity goes down. So we have to rotate the target in order to have a continuous beam. So in an X-ray tube, if the rotor is there to rotate the target, this is typically the rotating anode arrangement in the X-ray tube to give a very intense X-ray in a particular direction. So this is the arrangement of a rotating X-ray so that it continuously give the energy, and the power is related with the voltage we apply and the current, the electron beam current which is flowing. Okay, so if it is 40 kilovolt applied and 1 milliampere current flows, so the 40 kilowatt power is consumed by the X-ray tube, and that is available as a beam of X-ray. There are other advancements like a synchrotron radiation, in which we can generate a beam of X-ray which travels in a straight line, okay, with very high intensity, depending upon how the electron are stored in a ring in an accelerator. So we have got an electron accelerator which keeps on rotating in a circular form, and suddenly once they are bending at some wiggler, then we get beam of X-ray coming out. So this kind of arrangement is called synchrotron radiation. In India, we have got the synchrotron radiation facility at Indore, where the Indus one storage ring can have the low energy electron beam, and here the synchrotron radiations are ejected out in a beam line. This is how the experimental chamber looks like, where several beam lines are arranged in a straight line for doing the experiment. Well, by the bending magnetic field, we can have a different value of the magnetic field to have the storage ring in different radius, and we can vary the energy. So the photon having energy right from 1 keV to something like 40 keV, 50 keV, we can have from this synchrotron radiation source. So it's almost monochromatic. At the same time, it has a very high brightness, means very strong beam like laser which comes out. Okay, the divergence is very limited. So most of the radiation travel in a straight line for doing the fundamental research. Now, regarding the detection of these X-rays, initially Ranjan used the photographic plates, and normally it is called the shadowgraphy. When you are having a source of X-ray, your object is in between, and whatever is going out which cannot penetrate the object gives a shadow on a photographic plate. So this is called shadowgraphy. But in recent advancement, ionization detector are used to count the X-ray photon which operate at a high voltage. So using a GM counter, for example, one can detect how many photons are coming and study the scattering or a distribution. In the same way, we have a solid state detectors with multi-layers with the self-biasing to have the X-ray detection. And that is called the RVGs, radiographic video displays. So normally for the X-rays are being used by the scientists and engineers for the diffraction study, for the scattering study, for absorption study, and the photoelectron emission study for the elemental analysis or the composition analysis, and structure of the big molecules can also be done using these X-rays. Let me explain you through the model how do you get information about the atomic distribution using such a intense X-ray source. So this is a model which shows basically how the atoms are arranged. Okay, it shows a hexagon pattern. When I play, it's a dynamic model. So when we say that the atomic arrangement makes the material, so this is again a model, a crystalline solid with defects. This is how it looks like. When you see using the X-ray, where the wavelength is of the order of 1 angstrom, energy is something like 10 keV, and the interatomic distance is also of the order of 1 angstrom. So this X-ray beam can diffract from these lattice points, and give the diffraction pattern, for which the Braggs worked out the formula and got a Nobel Prize and found out the structures of different material. So this is a model in which the steel balls are there, and you see how fascinating it is. So in this model, the atoms are having size of the order of 1 mm, so that you can see with the visible eyes. Okay. And if you have a mixture of these two kinds of ball, this is how it looks like. Okay. And when you see the dynamic form, so this is a model, but in real systems for material research, different kind of atom are arranged in a different way, and how X-ray, which is having almost the same dimension as the interatomic distances, can give us all these images interplanar distances, and so on. So that has been a tremendous discovery of X-ray to get something for the material research, different material, medical research, health diagnosis, and security. Okay, so all these can be done using these X-rays. Let me give you some example. For example, sodium chloride crystal, ordinary salt. This is how it looks like, crystals, and atomic arrangement looks like this. How do you get all these? This you get using the X-ray. So if this is an X-ray diffractometer, you have a source of X-ray with a slit and another slit here, and the salt is placed here, and what you get is you have to move the detector, and as a function of angle you get a diffraction peak, and that gives you, using the Bragg's formula, you can find out what is the interatomic distance in a crystal. Okay, so this is a typical application of X-ray. For example, DNA molecule is a double helix structure, and this is how the diffraction pattern looks like of a double helix when you use this X-ray, monochromatic X-ray. And when you see the periodicity, you can obtain using this diffraction pattern. So these kind of information, even for DNA, the Nobel Prize was awarded for DNA structure. Even for carbon nanotube and structure of carbon nanotube, the Nobel Prize were awarded. Okay, the hexagon symmetrical graphene sheet are rolled in the form of tube, and this is how the fibrous tube look like, the hollow tube, single wall carbon nanotube, and this is how the diffraction pattern looks like. This is a scanning electron photographs, okay, and this is the diffraction pattern. So for material research, it has done a wonderful job, okay, the X-rays, monochromatic X-rays, and their distribution. For human body, for example, the X-ray source is there, and if you are in between, and this is the detector, and the image gives you all regular structure which we know of, or if there are defects in the structure that can be found out for the human body. We call it as a shadowgraphy. Okay, so this is typical the X-ray tube which is used to take X-ray shadowgraph or a photograph, we call it, and this is how the photographs look like. The transmitted beam of X-ray, if it is transparent through the muscles and so on, there is a bright patch, but where there is no transparency, okay, you get these dark spots. So the lungs can be identified, ribs can be identified, and so on. So this is basically the shadowgraph, okay, of a chest and a shoulder. Well, when you change the energy at low energies, then even the absorption from the soft tissues can be seen and identified, like detection of early stage of breast cancer can be done using a mammography machine, where the photographs give you the distribution, the density, and the order of growth of different tissues. In order to do the X-ray imaging very effectively, the fluoroscopy is developed. In fluoroscopy, a high-Z material like barium sulfide is injected or introduced in a body, and the contrast between the X-ray absorption between different tissues and the veins can be identified. Okay, and for example, in stomach or in intestine, if you want to identify the absorption, then one can use this fluoroscopy as a technique. All right, this is the typical photograph which you get from the fluoroscopy images. So the body parts can be mapped very easily using such fluoroscopic technique. And even the intestine and the lower part, body part, can be identified very correctly with these images. Even the blood clot can be identified using angiography technique. Again, you are having the X-rays and the the substance is injected and it diffuses within the veins, and we can get the digital subtraction method, okay, the transmitted and the absorption, to get the very sharp images. Well, the computer assisted tomography also uses it does X-ray, and the movement of detector in 3 dimension gives you the overall picture of the bone, the muscles, and the structure inside the body very effectively. And even the brain scanning can be done using the CT scan tomography, and even the stomach part can be identified very well using this tomography technique. In the tomography, the source and the detector, source is kept constant and the detector is moved to take the absorption in different direction to get a 3D picture on a 2D plane. So this is basically intensity scale of different tissues. Okay, for example, metal, the 100% absorption is there in metal. In air, there is no absorption of X-rays. So between these two scale, different material have got different absorption, and by measuring the intensity of X-ray using the digital counters, we can identify that this is the blood region, this is the soft tissues, and this is the other area of the fat and the lungs. So their the absorption power is different. Their density is different. Because of that, the absorption power is different. So using the same X-ray, by identifying, we can actually get the information about the structure of the human body. These days, security is a very stringent problem at international borders, and the transmission X-ray body scanner can be used to detect this siloed item or hidden part in the body or cavity of a person. So the X-ray source is there and a scanner plate is there to scan quickly the whole body part. So the normal structure and any abnormality within the body can be identified, and the person can be caught very easily by scanning. This is the conventional luggage scanner, baggage scanner, which is used at the airport, railway station, and any other places. Even at the temple, for example, you are carrying some arms and animation that can be identified along with the metal detectors. This is how the image of your baggage looks like. Because of the absorption power of X-rays of different material, you get this image very clearly. Even in the body part, for example, somebody has hidden the knife or the during surgical, some part is left inside the body. Then using these X-rays, we can identify the images. Even the drug capsule is somebody swallows and how it moves within this intestine, that can be traced out. And even in the abdomen or the intestine lower part, okay, the absorbed drugs can be identified. Well, so what is the future of X-ray imaging these days? So what is the advancement is the portable dental and the fluorescent for elemental distraction. So the source of X-ray is also made portable, very small and handy. Even the detector has also been developed very small and handy. No photography is required, and immediately you get a picture. And even elemental analysis can be done using this X-ray, and that is called the fluorescence analysis of these elements. Okay, you shine with high energy X-rays and you get a characteristic X-ray coming out, and you can identify different elements. So that is the future direction, and the researches are taking place. Now, in all these modern technology, the X-ray source is very small. Now, how X-ray source can be so small? Because of the recent development in the electronics. Earlier, the high voltage supply, which was used for the X-ray production, was having a size of the order of a room to generate 40 kV or 50 kV. Even now, in hospitals where we are having a big machine with lot of lead shielding, you are having a separate room, X-ray room. But here in this hand X-ray machines, you have a very small tiny source with the battery operated power. It can take power and generate a high voltage, something like 40 kilovolt or 50 kilovolt in a very small unit. And the X-rays are emitted instantaneously as you press the button, and the detector is also very small and semiconductor detectors, so that we can measure the energy of the X-ray with the energy resolution of 0.1 kV. So different element differentiate their characteristic X-ray by zero point 0.5 kV or so. So we can identify different elements which are present in a material or human body by the detection. So with the same probe, we can excite the material and detect and get the image. That is the power of X-ray fluorescence analysis and the technology which is coming up. So this is the device, and this is the electronic monitor. An electronic monitor with the software gives you the complete data that what are different elements present in a given material. For example, silicon oxide, you will be having a silicon and the oxygen present. In aluminum sulfate, you will be having aluminum, sulfur, and so on. If you are having a gold, you will have identification of a gold. So even the chemical analysis can be done along with the images and the distribution. Okay, so all these are the central processing unit, and it is Wi-Fi enabled. Okay, so whatever data you are scanning or taking from the field, you can transfer to the relevant place. For example, research laboratory, you can transfer the data, or the hospital, you can transfer the data from the accident site. So these are the new technologies which are coming up on X-rays. After discovery of the X-rays, even the camera is coming using the X-rays. We have having a sealed X-ray tube, and with a small opening, it gives you the shower of the X-ray. And the reflected X-ray are detected at the same unit, and the back you are having the image, okay, of the human body. So with the same source and the detector like camera, we can have image of the human body or the interior of the human body. So these are the advancements which has taken place in about 100 years or 125 years after discovery of the X-ray. So what we are looking forward to now, that the X-rays are so useful for the human body that even a high voltage can be generated in a very small unit, okay, with intense beam of about 2 milliampere. So this much power we can have from the lithium polymer battery, which is rechargeable again. And we can take at least 100 shots, 100 X-ray shots can be recorded on such a compact and small device. And we are having a LCD display which can give you the image as well as the constituents of these images, that what are the constituents of the body. So what we like to thank basically the inventor who has invented Willman Röntgen, the X-rays, and all those others who have made the X-ray useful for the mankind. Okay, so this is such a useful tool that everybody can make use of this X-ray, whether it is a material scientist or it is a health scientist or it is a security person. Okay, so it's a wonderful tool, but the caution is we should limit exposure to the normal tissues. Okay, and one has to get a training to utilize these X-ray sources. Authorized person can use these X-ray sources, because excessive dose of this X-ray is not good for the health or for the normal tissues. So what I like to sum up and conclude that this is a wonderful time for all of us. Even these COVID situation, if you take X-ray of lungs, and by the intensity analysis, recently they have developed the software that even you can identify the infected, COVID infected patients using this X-ray machine. And that is what the effect of the wonderful invention of the X-ray, which has gone long way, right from the material research to the human body and the security, uh, and the present situation where we don't know how the COVID is being affected, how we take lot of time to identify the COVID infected patients. But the X-ray machine can do the wonder and give the information instantaneously. All right, and at very low cost. Like for example, X-ray, which we are using in normal hospitals, they charge only 100 rupees for any X-ray photograph. So from the same photograph, using the software, you can do the exposure analysis, the intensity distribution, and get the information about the COVID affected patients. So that's the great power of the X-ray. Okay, so I like to stop here, and thank you so much for giving this opportunity and a time. I wish I could share my experience and information with the young ones and the teachers and the scientists who have joined the lecture. And I'll be happy to share if there are any questions quickly. Yes, Suresh.
Yes, sir. Anyone having any question from our Google Meet? Sir, one question I received just now.
Yes, please. Mhm.
ये क्वेश्चन है सर, आपने जो भी 2D एटॉमिक कॉन्फ़िगरेशन विजुअलाइजेशन के लिए एक वीडियो दिखाया,
वीडियो
उसी के
दिखाया है,
रिगार्डिंग
हाँ.
है सर, कि इज़ इट
Okay.
पॉसिबल इन 3D आल्सो?
In
In
CD,
any other experiment or?
in 3D, it is difficult to visualize using the optical imaging. But certainly, if you have this kind of model, okay, then you can get a feel. All right. So such model you can make, design, and visualize where is the spacing and so on. Okay, this is a 3D model. Can you get a feel?
Yes, sir.
Visible?
बट सर शायद उनका क्वेश्चन इस तरीके से था जो ऑटोमेटिक जनरेट हो रहा है स्ट्रक्चर, उस तरीके से ऑटोमेटिक जनरेट होकर के दिखाया ऐसा कुछ सिस्टम इन
वेल
3D।
ये ऑटोमेटिक जनरेट हो रहा है, यस, व्हेन आई हैव अ 2D एंड आर पार अपन नेकेड आई से देख पाते हैं.
Yes, sir.
Okay, we can see it with the naked eye, but certainly it happens in 3D also. What you have to do is section out and then look at it.
Yes.
Okay.
और सर अभी एक क्वेश्चन और आया है फ्रॉम फेसबुक
Yeah.
पेज, एनसीएसएम फेसबुक पेज, कि पहला एक्सरे किस डेट को डिस्कवर हुआ? ये मतलब
पहला
एक
एक्सरे इनफैक्ट सोसाइटी
I
के
think
लिए सोसाइटी के लिए तो इट केम आफ्टर द आई थिंक 1995 के बाद जो फोटोग्राफिक टेक्निक है.
सर ये
Okay.
जो मैं जस्ट एक चीज रखना चाहता हूँ इसमें सर, जो
जी.
रोंजन के द्वारा अपनी जो वाइफ ब्रथा का एक्सरे लिया गया, उसको फर्स्ट एक्सरे मान सकते हैं? Just
हाँ,
44
ऑफिशियली
days.
जो उन्होंने डिस्कस किया.
Yes, sir.
ओके, एंड वो इन्वेंशन से जुड़ा ही हुआ है.
Yes, sir.
राइट.
Yes, sir.
ओके,
And
सो उस समय एक्सरे सोर्स भी अवेलेबल नहीं थे इजीली.
yes, sir.
ठीक है, तो पब्लिक के लिए व्हेन इट केम, सो प्रोबेबली आफ्टर in the beginning of 19th century it came to the public for the diagnosis purpose. क्योंकि शुरू में tuberculosis was one of the first disease which was identified by the X-ray, chest X-ray. Okay.
सर जस्ट एक क्वेश्चन और अभी रिसीव हुआ है.
जी जी.
ये एक्चुअली सर तीन चीजों को कनेक्ट करके क्वेश्चन पूछा है उन्होंने, कि जिस तरीके से अपना ऑप्टिकल माइक्रोस्कोपी है, उसमें जो हम विजिबल लाइट्स को यूज करते हैं, उनका जो वेवलेंथ है उसका
वो
रेंज
400 500 नैनोमीटर.
यस नैनोमीटर, और वी कैन से 4000 टू 7000 एंगस्ट्रॉम इन एंगस्ट्रॉम,
आर्मस्ट्रॉन्ग.
और एक्सरे का रेंज लिखा 1 एंगस्ट्रॉम. तो ये बोल रहे सर जिस तरीके से मतलब ये एंगस्ट्रॉम रेंज बढ़ने से पहले हम जो मतलब ऑब्जेक्ट जिस साइज के ऑब्जेक्ट देख पा रहे थे, एक्सरे से उससे क्रिस्टल स्ट्रक्चर हम देख पा रहे हैं, और इलेक्ट्रॉन माइक्रोस्कोपी की अगर बात करें तो उसमें सर और स्मॉल लेवल पर, स्मॉल स्केल पर जाकर के हम मतलब ऑब्जेक्ट को स्कैन कर सकते हैं,
देख पाते हैं,
देख पा रहे हैं, स्कैन कर पा रहे हैं, या उनकी मतलब प्रॉपर्टीज क्या है वो ले पा रहे हैं. तो क्या सर इनको एक वेवलेंथ के एक सीरीज के रूप में देखा जा सकता है कि दिस वन इज फर्स्ट, सेकंड, थर्ड साइज बेसिस?
बिल्कुल बिल्कुल सही है, बिल्कुल सही है. बिकॉज इवन इन ऑप्टिकल माइक्रोस्कोपी, ठीक है, अपन ब्रॉड रेंज काम में लेते हैं. इसकी जगह यदि अल्ट्रावायलेट ले, देन वी कैन स्टिल सी स्मॉलर देन 500 नैनोमीटर. ओके, ऑब्जेक्ट्स. ओके, और उसकी जगह यदि हम एक्सरे लें, देन सर्टनली वी कैन प्रोब. बट द क्वेश्चन इज यू हैव टू डिटेक्ट द एक्सरे, स्कैटर्ड एक्सरे. ओके, ऑप्टिकल में तो आई टेक्स केयर because eye is sensitive. Right? So you have to convert, and then the resolution is decided by the two factor. Okay, the wavelength and the detector resolution, whether detector can resolve it or not. So certainly in electron microscopy, when we have the electron beam, the wavelength is of the order of 0.1 or 0.01 Armstrong, so that you can see the atomic dimension very precisely. So, for example, 1 millimeter ball I have used in this model. Okay, the same model is can be seen of a silicon monocrystal. Okay, using the electron microscopy. The same grain boundary, defects, vacancy. If you take a silicon wafer and do the electron microscopy, there the magnification is of the order of 10⁻⁷. So 1 Armstrong becomes a millimeter. Okay, all right, and My model is also 1 millimeter. Okay.
Yes, sir.
Yeah,
Sir,
correct.
Samiksha Shekhawat from NMPG College, Hanumangarh. इनका क्वेश्चन है सर कि सर आई वुड लाइक टू आस्क व्हाट वाज द प्रॉब्लम फेस्ड व्हेन एक्स-रे वाज नॉट डिस्कवर्ड.
Well, when X-ray was not discovered, it was very difficult to differentiate between the crystal and non-crystal material. Okay, it was vaguely described by the change in the melting point. All right, whether it was sharp, then it was metallic, using the other properties. But once the X-ray was discovered, they have correlated most of the properties with the structure. So that was very important from the material science point of view. Even for the medical diagnosis and research, when X-ray was not there, people were trusting on the human intervention only. Somebody used to say, मेरे को ये तकलीफ है, मेरे को यहाँ तकलीफ है. Okay, and the doctors were only observing and feeling and suspecting that there may be a damage inside the bone or injuries, and they were suggesting the treatments. Okay, so it was more on speculation basis, but with the X-ray, things have become very definite, visible, and reproducible and quantitative. Okay, so the tool is a wonderful tool, and from the source point of view, there has been a lot of advancement, and the detector point of view also there are lots of advancement. Okay, because these days you are having a very tiny detector which can detect X-rays very effectively. All right, for example, when you go to the dental uh, X-ray, earlier it was very difficult. He used to take 2 hours to get a picture and ask you next time, but here they put RVG inside and just click it, okay, and get the image, and the image is ready on a computer, and he can magnify and show it to you. If it is not proper, then he can go for another shot. Okay, it doesn't cost much, so it's a reusable detector every time. Okay, semiconductor based detector. Earlier it was the photographic detector, and they have to etch it, for example, silver nitride one. So they have to process it, take it in a dark envelope, take it out, and then if he has to make a correction, he has to redo the process every time. Okay, so the situations has changed drastically.
Sir, one more question
Yes,
from
please.
Rajashree Bhattacharya ji from
Mhm.
Kolkata. Is there
Good.
any adverse effect of X-ray on human body?
Uh, yes, because this is an ionizing radiation, and certainly excessive dose is no good for normal human being or normal function of the tissues and the cells. So even the operators which are using this X-ray for your diagnosis, they are having some lead shields and a proper take care. They go away when with the remote control of all these X-ray machines. Okay, so one has to take care because it's not safe. Yes, so that precaution is always there, that you should have minimum exposure of these radiation. All kinds of radiation, what you talk of these days, even the microwave radiation, are not safe, you know, at higher dose. So the safety is related with the dose, because we are treating the cancer with these radiation these days.
सर कुछ छोटे-छोटे क्वेश्चंस और आ रहे हैं. सो
Okay,
एक क्वेश्चन है
I'll be
फ्रॉम
happy.
साजिद मोहम्मद. अ,
Hmm.
साजिद मोहम्मद क्वेश्चन है, सर ह्यूमन बॉडी में भी कोई ट्यूमर हो तो उसका भी पता लग सकता है क्या एक्स-रे से?
Uh, जैसा मैंने एक लिस्ट दी कि there is a variation in the density. So normal जो फंक्शनिंग या ब्लड फ्लो रहता है उनकी डेंसिटी और ट्यूमर इफेक्टेड एरिया की डेंसिटी उनमें फर्क हो जाता है. So when you do a contrast analysis, then you can identify the location of a tumor, and of course the distribution gives you approximately the size of the tumor. Yes.
Sir, one question from Jaga Dhaku. Can carbon compound block X-ray waves?
Well, only low energy X-ray can be blocked by the carbon. The high energy X-ray cannot be blocked. For high energy X-ray, you need lead shielding, basically a high Z material for shielding, because carbon compounds are low Z compound. Okay, they cannot absorb photons having energy 6 keV, 7 keV, and so on. Okay, they are transparent. So, like jellyfish, okay, things are transparent. So, X-rays, a human body is transparent. Flesh, for example, blood, water, they are transparent, very little absorption. So, if there is a tumor, if there is a variation in the density, then you can find out the difference in the intensity or the contrast.
Sir, one more question from Dr.
Okay.
Ramesh Chand. Why only iodine is used as a contrast material?
Well, iodine is a high Z material which is easily soluble or dissolvable. Okay, iodine makes compound very easily with water. All right, so it can disperse very easily and give you a very good contrast. Barium and iodine, these are the material which are used for human body.
Sir, one more question from Kolkata. Can we get 3D view of objects using X-ray?
Yes, the tomography is the technique when they have to move the detector, keep the patient at one place, all right, the source at one place, and move the detector. You get intensity variation, and the 3D image is reconstructed. Okay, even in CT scan. So there are planes in which the absorption is measured in different plane, and from that the 3D image is reconstructed.
One more question, sir. क्या एक्सरे से कार्बन कंपाउंड डिटेक्ट हो सकता है?
एक्सरे से कार्बन कंपाउंड एज सच डिटेक्ट नहीं होते हैं, बिकॉज कार्बन की जो केशल एनर्जी है इट्स वेरी लो, so it's not getting excited or it's not absorbed. Okay, but certainly जो ड्रग्स हैं जिनमें नाइट्रोजन होती है मोस्टली, okay, so along with the carbon, if nitrogen is there, so those are detectable. Okay, so one has to use really low energy or a source with very thin window so that the low energy radiations are there. So from there you can vary the contrast and get a feel of the drugs.
Sir, one more question from Sajid from the
Yes.
Science Academy Rawat, sir. सर, नेचर में कोई ऐसा क्रिस्टल भी है क्या जिसकी इंटर एटॉमिक डिस्टेंस एक्स-रे वेवलेंथ ऑर्डर में ना हो? अगर ऐसा क्रिस्टल है तो उस पर एक्स-रे से हम उसकी स्ट्रक्चर पढ़ सकते हैं या नहीं?
वेल, नेचर में ऑर्गेनिक जो क्रिस्टल होते हैं, ऑर्गेनिक क्रिस्टल्स, उनके अंदर इंटर एटॉमिक डिस्टेंस ज्यादा होती है. ओके, फॉर एग्जांपल डीएनए है. सो डीएनए में जो स्ट्रक्चर है वो लो एनर्जी एक्सरे से देखा जाता है व्हेन द वेवलेंथ मैचेस विद द इंटर एटॉमिक डिस्टेंस. फॉर एग्जांपल कॉपर है तो कॉपर तो 9 केवी दे रहा है, तो उसका एक 1.5 आर्मस्ट्रांग है. तो नॉर्मली around 1.5 angstrom you can identify, but with the conventional X-ray you cannot identify DNA. So in order to identify the DNA structure, you need soft X-rays, okay, low energy X-rays, so that the wavelength is large and interatomic distances can be monitored. So it's a very right question, relevant question.
बिल्कुल सर,
Right
और
now,
डीएनए एक्सरे को लेकर भी
जो ये
नोटिफाइड।
मशीन्स हैं, सिंक्रोट्रॉन रेडिएशन
यस सर।
मशीन जो है इंदौर में, which is a Indus 1 for the low energy soft X-rays and Indus 2 for higher energies. So all these metallic and other compounds, oxides, ceramics, unke liye Indus 2 is useful, and for low energy, all these polymers and hydrocarbons, this Indus 1 is used. Okay.
सर क्वेश्चंस बहुत सारे हैं, बट टाइम लिमिटेशंस के कारण हमें सेशन अभी यहीं
Okay.
विराम देना पड़ेगा सर। और
they can send on an email.
यस सर।
Okay.
यस
You
सर।
can share my email to them.
बिल्कुल सर, हमें मेल कर सकते हैं या सर को डायरेक्ट मेल कर सकते हैं, आपको आंसर मिलेंगे
Yes.
आपके क्वेश्चंस के निश्चित रूप से।
जरूर
और
जरूर जरूर।
जिन क्वेश्चंस को हम यहाँ प्लेटफॉर्म पर नहीं लेके आ पाए हैं, उनके लिए सॉरी कहेंगे, क्योंकि समय की सीमा को देखते हुए हम सभी क्वेश्चंस को नहीं पढ़ पा रहे हैं इस प्लेटफॉर्म पर। और जितने भी साथी हमसे आज जुड़े इस प्लेटफॉर्म पर, और 125 इयर्स ऑफ एक्स-रे सेलिब्रेशन में हमारी टीम का हिस्सा बने, उन सभी को रीजनल साइंस सेंटर गुवाहाटी, नेशनल काउंसिल ऑफ साइंस म्यूजियम्स की ओर से मैं सभी का हार्दिक आभार व्यक्त करता हूँ। और अंत में फिर से मैं कहना चाहूँगा कि अपना बहुमूल्य समय देने के लिए प्रोफेसर वाई के विजय, जिन्होंने हम सभी की जितनी भी सेशन के बाद जो क्वेश्चंस थे, जो हमारी जिज्ञासा थी, उनके लिए भी समय दिया, और एक समय दिया हमें इस प्लेटफॉर्म पर आपस में जुड़ करके एक्स-रे के 125 साल को सेलिब्रेट करने के लिए। तो थैंक यू वेरी मच सर।
Suresh ji,
Yes, sir.
we must be thankful to our good friend from Chile.
Yes, sir.
Patricio, namaskar. Thank you so much for being with
Sir,
us.
may I request your friend to say few words?
Yes, Patricio, you can switch on your mic and speak something. It's
Just
right now.
on your mic, sir.
You can switch on your microphone.
Sir, switch on your mic. Sir, your audio is off, sir. Maybe
Please unmute your mic. I think offline हो गया क्या?
maybe sir, some
Okay.
connectivity here. Okay, sir.
All right.
Once again, thank you very much.
Once again,
And
thank you. Thank you.
yes, sir.
Yes. How are you? Can you unmute your mic, please? Yeah. Please unmute your mic. It was good. Thank you.
Okay, sir. Thank you. Thank you very much, sir.
Okay. Bye bye.
Bye.
चलिए बढ़िया, इसकी रिकॉर्डिंग उसी लिंक पे मिल जाएगी।
सर ये लाइव थे, हम ऑलरेडी अवेलेबल है सर, यूट्यूब
लाइव थे।
ओके, थैंक यू
अवेलेबल। ओके, थैंक यू सो मच। ओके, गुड।